Okay, I hope I'm audible and welcome you all to the last interactive session of the course Viscous Fluid Flow. And today, this is an extra session. Our normal interactive sessions were over by last Saturday, where we looked into the stability analysis of inviscid parallel flows and we were in the regime. So if you remember, and if you had gone through the videos and the lecture notes meaning the notes of the interactive session, and also the lecture notes of the week's contents on instabilities, you might have seen that we were in the regime of linear stability analysis, where our objective was to write equations for the perturbations which were present to the base flow that we considered. So the hallmark of linear stability analysis that we saw is that we could write the perturb variable in terms of their normal modes, where we tried to study that how do we basically write normal modes for this perturb variable and what is the essence behind these normal modes. And we looked into something which is known as the Fourier transform, although we didn't go heavily on it, but the very essence of writing the normal mode as in the form that we saw comes from the fact that each individual modes of the wave numbers behave independently, and they spans from minus infinity to plus infinity, which is the basis of Fourier transform basically. And then so what we got by writing the perturb variable in terms of the normal modes was that our PDEs, which govern the linearized perturbation equations, and I say linearized because we discarded the non-linear terms again, since we are in the domain of linear stability analysis. Okay. And then by substituting the form of normal modes in the governing equation for the which governed the perturbations, which were linear, we got certain ODEs, and then our objective was to solve for the ODE. But then we saw that we basically got four ODEs, which was, so first of all it was the continuity equation, and then it was subsequently followed by the three momentum equation in the x, y, and z direction. But we used a very powerful theorem which we call it as the squares theorem, which says that if the wave numbers are the same, then a 2D disturbance for a parallel or a nearly parallel flow in an inviscid fluid, which also can be extended. This theorem can also be extended for viscous flows as well. It says that if the wave numbers are same, then a 2D disturbance is more powerful than a 3D disturbance. Okay, which means that if we are only trying to assess the stability of the system, it suffices just to consider a 2D disturbances instead of considering the 3D disturbance. But it must be very clear that if someone asks me to calculate the 3D flow field of the perturbations, then of course we need to solve the entire 3D problem. Okay, but we were only interested in whether the perturbations that are present in the flow, will they grow or decay with time. That is we are just interested in their growth rate. It suffices to just consider the 2D problem, because by Square's theorem it says that the 2D disturbances are stronger than 3D disturbances. So if there are perturbations and if they grow with time, it is sufficient to see the 2D problem to conclude whether those perturbations will decay or grow with time, basically. Okay, and then the advantage that we got when we reduced the 3D problem into the 2D problem is that we could use stream functions, because now we have the two components of velocity u and w, if you remember. And then we define a stream function psi prime as in terms of normal modes, as we did for the velocity components and pressure. And what we did is we tried to establish the relationship between the perturb velocity component and the perturb stream function by using the traditional velocity stream function relation, in which we saw that the continuity equation was trivially satisfied. And then when we established the link between the eigenfunctions of the respective velocity components and the stream function, we eliminated pressure, and then use those relations of the eigenfunctions of the stream functions and the velocity component. We single what we got is we got a single equation which governs the stability of the problem, to be precise. And that equation, which you can see on your screen, is the Rayleigh stability equation, where if you remember, this capital U is the base flow, the knowledge of which is completely known to us. C is the eigenvalue that we are trying to seek, which will dictate. In fact, we have established that the imaginary part of eigenvalue will dictate the stability of the problem. That is, if Ci is greater than zero, okay, this means that the given base flow is unstable, and if Ci is less than zero, it says that it is stable. Okay, and Ci equal to zero is the case which we call it as the neutrally stable system. Uh, but yeah, so it is the value of C. In fact, it is the imaginary part of C which will dictate the stability of this problem, and the corresponding eigenfunctions of which we are trying to solve for is phi, which is the eigenfunction of the string function that we considered basically. Where these alphas, if you remember, these alphas are the wave number that was present in the x direction. So where I mean, this alpha is the generic wave number that we considered in the x direction. Okay, so this is where we end today, and then we saw that this equation, that is equation 14, this is indeed homogeneous, and then we looked into the boundary conditions that is being satisfied by the velocity field, where we saw that there is only one boundary condition now, since we are in the inviscid analysis, since you're doing an implicit analysis. So it's just the no penetration boundary condition that we use, and the result of this boundary condition was that we got that phi at the domain boundaries was equal to 0. So it was a homogeneous boundary conditions that we got, that is shown by equation 14, and the homogeneous boundary conditions. There are two homogeneous boundary conditions to be precise. Typically, because this is a second order problem, so we just require two boundary conditions, and this indicates that it is indeed an eigenvalue problem that we are essentially looking for, where we are trying to solve for this corresponding eigenvalue eigenfunction pair, okay, which will eventually dictate the stability of the problem. Okay, so this is where this is where the analysis of the Rayleigh stability equation was completed. And then, just for a head start, what I said is that, now how can, now given a base flow, for instance, given that we are given, we have a base flow which is already known to us. Let's say capital U of Z is known to us. How can we use the Rayleigh stability equation to analyze the stability of this base flow? Okay, although we have not yet solved the entire Rayleigh stability equation, and I would say that this is beyond the uh, reach of this course. But there are certain criteria which uses the Rayleigh stability equation to assess the stability of certain base flows. Okay, and one such criteria that we little bit discuss, and from where we will take it up from today, and it is where from we'll take it up from today, is known as the Rayleigh inflection point criteria, where the goal was that we seek how does the Rayleigh stability equation assess the stability of a given base flow. That is something that I already stated just now. So the Rayleigh inflection point criteria stated that, and this is where we stopped it in the last class. So it says that a necessary condition for instability is that given that we have a base profile, the base profile must have at least one inflection point. Okay, meaning that at least in between the domain, let's say Z0 to 1, there has to be a certain value Z0 which lies between 0 to 1, where U double prime of Z0 is equal to 0, which is the very definition of an inflection point. Okay, and if this criteria is satisfied, it says that there could be the possibility of instability in the given base flow. Okay, but remember, this is a necessary condition. But I would say, but not sufficient. Okay. Okay, so this is what the Rayleigh inflection point criteria says, and although we have not done it, but there is so this proof of the Rayleigh inflection point criteria, this can be done if we start off from this Rayleigh stability equation. And what you need to do is you need to integrate this Rayleigh stability equation throughout the domain, and you need to basically take the complex conjugate. You need to multiply this by the complex conjugate of phi, and then integrate it throughout the domain. And then, doing some algebra, after some algebra, you can argue that for instabilities, there has to be one inflection point, that is, this base flow, the given base flow u has to change sign, uh, sorry, it's not the given base flow, but so it's like, the gradient of u prime has to change sign within the given domain, which indicates the presence of an inflection point mathematically. Okay. uh, yeah, and this is where we stop, and today, like, we will take a certain examples, a very simple example, in order to understand this Rayleigh inflection point criteria in a better way. And thereafter we'll look into a more stronger criteria, because this is not a sufficient criteria, so we'll look into a stronger criteria to assess the stability of the considered base flow. In fact, we'll look into two criterias. But yeah, so this is where we stop. Then as we do, I'll stop. I'll pause for a couple of minutes, and so the floor is open for discussions. But we'll take it up from here. Okay. And as I said, the goal is, once we are done with this criteria, what we'll do is we will very briefly see methodology. We'll briefly see the methodology for solving an eigenvalue problem, just to formally finish the task that we had. That is, how do we basically, so once we get the Rayleigh stability equation, how do we solve this? Although we'll not solve the Rayleigh stability equation, we'll not solve the exact Rayleigh stability equation today, because that equation is somewhat more complex. I will just give you a flavor of by taking a prototypical eigenvalue problem, and then I'll show you how to basically solve this eigenvalue problem. The same methodology can be applied when you try to solve the Rayleigh stability equation, at least numerically. Okay. All right. So let's just finish this criteria first. So in order to understand the Rayleigh inflection point criteria, let us take an example. That Let us consider a simple Couette flow and try to assess the stability of Couette flow by using the Rayleigh inflection point criteria. So the example is that we'll try to assess, sorry, we'll try to assess the stability yeah, kindly check the spelling. I just got confused. I think this is one S. Yeah. Anyways, okay. So we try to assess the stability of Couette flows. So as we know, the Couette flow is just it's just created by the motion of one plate with respect to one another. So for instance, if I have a plate, for instance, like this, let this be the x, let this be the z, and then if I move this plate with some velocity, let's say, so yes, so how do we say, okay, let's move this plate with some velocity u, that's a given velocity. Then you know that the flow field is basically, or let's say I name this velocity as up, which is the velocity of the plate. And then the flow field basically looks something like this. So if I non-dimensionalize the system, so if I kind of non-dimensionalize my system, my velocity field would look something like this. Okay, so I consider my characteristic velocity uc as up, and then the flow field, that is u of z, would basically be equal to z. Okay, that is typically because I have non-dimensionalized it with the plate velocity, which means that so this is the point z equal to 0, and this is the point z equal to 1, because this is the channel height, okay, that I have considered, and my given length scale, of course, is also equal to h, which means that this velocity at z equal to 1 is just 1. Okay, and then we have a linear velocity profile, which is the typical velocity profile of Couette flow, which means the given base flow has this profile because we are considering a Couette flow and we have non-dimensionalized it with the plate velocity. Okay. Now the question is, so this, so I think so far is fine. We are just writing a non-dimensionalized version of the Couette flow. Okay. Uh, Now so the question that we are trying to answer is that given this base flow, how can we predict whether this given base flow is stable or not using the Rayleigh inflection point criteria? So the Rayleigh inflection point criteria says that somewhere within the domain, if I have an inflection point somewhere within this domain, then there could be instabilities in the flow. Okay. So the condition of the inflection point. So the inflection point by its definition is the fact that d2 u of z by dz2, this is basically what gives me the inflection point. And in fact, if you calculate it, that this is equals to 0 because of the fact that my velocity profile is just linear. Okay. And since this is 0, since u is basically equals to z, and that's the reason why it is 0. This means that indeed the Rayleigh inflection point criteria is satisfied. Okay. So this means that because Couette flows, so since it's a linear velocity profile, each point within the domain is an inflection point. This is something that you can infer. Okay. So since the profile is linear, you can say that each point within the domain is an inflection point. Okay. Which means that the Rayleigh inflection point criteria is satisfied. Similarly, you can take any arbitrary flow. For instance, you can take a parabolic flow and then check that the Rayleigh stability inflection point criteria is satisfied or not. Okay. Now, this indicates that there could be instabilities, but it's not. Remember, it's not a sufficient condition. So this indicates that there could be instabilities in Couette flows. Okay. So in order to have a stronger criteria, sorry. So in order to have a stronger criteria, so we'll look into one more, in order to have a stronger conclusion of instabilities, I would say we'll look into one more criteria, and this is known as the Jortov's criteria. This is known as the Jortov's criteria. Okay, I think there are two dots over here. Please check the name of once again. So what Jortov's criteria says is that a necessary condition for instabilities is that u double prime into u minus u naught, this has to be less than 0, okay, somewhere in the flow field. In the flow field. Okay, where your u naught is basically your u at z equals to 0, z equal to z naught, where your z naught is the inflection point. It's basically your velocity at the inflection point. That's it. So what Jortov's criteria said is that once again you can prove the Jortov's criteria from from the Rayleigh stability equation itself. So what it says is that you evaluate this quantity, and if this quantity is less than 0, then it's a stronger criteria. Although this is not a sufficient criteria, it's a stronger criteria for instabilities. I say it's stronger because you can apply this now for Couette flows. So if you apply this, so applying for Couette flows. So if you evaluate this quantity for Couette flow, u double prime into u minus u naught, where you have u equal to z, Okay, this quantity come out to be equal to 0. Since why this is 0? Because we know that u double prime is equals to 0 for quiet flows. Okay, for quiet flows. This means since this term is 0, therefore Jordauf's criteria is not satisfied, because Jordauf's criteria says that for instabilities this term has to be less than 0. But we saw that for quiet flows this is exactly equal to 0, which means that Jordauf's criteria is not satisfied. Okay. Jordauf's criteria is not satisfied, which means that quiet flows are stable. Okay, that is something that you can basically infer. So therefore quiet flows are inherently stable. Okay, quiet flows are stable. That means you add any perturbations, I would say any small perturbations, because we are in the regime of linear stability analysis. So you add a small perturbations to the base flow. Small meaning that the magnitude of the perturbation should be less than the magnitude of the base flow. If you add such kind of perturbations, okay, in a quiet flow, the perturbations will eventually decay, because from the Jordauf's criteria you have seen that you have basically seen that the given base flow is essentially so I would say it's not the base flow, but this term u double prime into u minus u naught, this is 0 for the chosen base flow that we considered. And since this is 0, the Jordauf's criteria is not satisfied, which means the quiet flows are always stable. Okay, so I hope this is clear. So applying these criteria are easy, but their proof is little bit cumbersome. But if you are interested, I can show them separately. But let's not go into the proof of these criteria. But the hint for the proof is that it comes from the Rayleigh stability equation only. You integrate the Rayleigh stability equation and then multiply with the complex conjugate of phi basically. And then after some algebra, you can assess these stabilities. Okay. All right. I hope this is clear. Then finally, there is one more criteria which is known as the Howard's semicircle theorem. So once again, I'll not prove the Howard semicircle theorem, but I'll just give you the statement. So what it says is that for unstable modes or wave numbers, C, which is the eigenvalue, must lie in the semicircle given by, so it's given by this. Okay, so this is the equation of semicircle, uh, where C must lie in order to have instability in our problem. Okay, where this semicircle is just this CR, where CR is the real part of C, U max plus U mean plus Ci square. This should be less than equal to half of U max minus U mean whole square. Okay, so this is the equation of the semicircle where C must lie in order to have instability. Okay, where this U max is actually the maximum value of the velocity profile inside the velocity for the velocity profile. So it is max of U, and U mean is just mean of U. So once you know the base flow, you can calculate U max and U mean, and then you can calculate this quantity. You can also calculate this quantity. For instance, if I just draw this schematic of this, what you will see is that if I plot, Ci versus Cr, okay, then for instabilities, there will be a semicircle. There will be a semicircle where, the center of this semicircle, this the center is basically this term, half of umax plus umin. This is the center. This is, this is half of, umax plus umin. Okay. And then this radius is half of umax minus umin. Okay. Which means that if your Ci, okay, lies inside this semicircle, for instance, in these points, let's say, then this zone, then this will indicate instabilities. Okay, so these points, so if Ci lies inside the semicircle, this will indicate instability. In fact, this is a sufficient condition to to see if there are instabilities in our analysis. For instance, for the Kuwait flow, if you calculate, you will see that your Ci doesn't lie. If you happen to calculate the eigenvalue C, okay, your Ci should not lie, so for instance, if you want to calculate for Kuwait flow, your Umax for Kuwait flow is 1, your Umin is basically equal to 0, okay, which means that this term will just become to be equal to 1, and this term will also become to be equal to 1. So for the Kuwait flow, you can simply draw the semicircle here, and you will see that your C will not lie inside the given semicircle because your Kuwait flows are basically stable, okay. But if your C, in fact, to be precise, it's the Ci, okay. But if the Ci lies inside the semicircle, then this is a sufficient condition for instability, that at least there will be one unstable mode that will be present in the problem. If there is one unstable mode, then your problem is, then your base flow is unstable, because since every modes are generic and independent of each other, and if any one of the modes are unstable, that means your given base flow is unstable, okay. And this is what the Howard semicircle theorem says, okay. All right, so these are the three criteria that I wanted to discuss. Just for a recapitulation, we had the Rayleigh inflection point criteria, which says that a necessary condition for instability is that within the domain, the given base flow should have at least one inflection point, okay. And then we saw that if we take a Kuwait flow, since it's a linear flow, each and every point inside the domain is an inflection point, which means that the Rayleigh stability equation is satisfied. Sorry, the Rayleigh inflection point criteria is satisfied. And then we saw that the stronger criteria, which is not still a sufficient criteria, but it's a stronger criteria to the Rayleigh inflection point criteria, is the Jorda's criteria, which says that for a given base flow to be unstable, this quantity this u double prime into u minus u naught, this should be less than 0 somewhere inside the flow field, that is inside the flow domain, okay, where u naught is the velocity of the base flow at the inflection point. And we saw that for Kuwait flow, this quantity indeed came out to be equal to 0, which is not which indicated that the Jordan's criteria is not satisfied, meaning that the Kuwait flows are inherently stable, okay. And then we looked into a theorem which is known as the Howard semicircle theorem, which says that if you have an unstable, which says that for instabilities, the wave numbers should, for instabilities, that is, in order to have at least one unstable mode, which will of course indicate instabilities, the eigenvalues, in fact, the imaginary part of the eigenvalue should lie within the semicircle, which has the center half of umax plus umin, comma 0, and the radius half of umax minus umin, okay. And if the eigenvalues, that is the imaginary part of the eigenvalues, lie within this semicircle, then we can see that there is at least one wave number which is unstable, and this is sufficient to say that the given base flow is unstable, okay, because we are in the regime of linear stability analysis, where each modes behave independently with respect to one another, okay. All right, so this ends the stability aspects of the hydrodynamic problem that we consider, that is the inviscid flows, inviscid parallel flows, where we are trying to assess the stability. And with this, we end this. As I said, there are so this is a very, very, very big domain of fluid dynamics. That is, the stability analysis, where you can carry out numerous analytical treatments of various instabilities. For instance, there is something which is known as capillary instabilities, as I said in the previous class, that so for instance, when you open the kitchen sink, you will see that there is a laminar jet that is coming in. After that, into which the jet breaks down into drops. So this instability is actually driven by surface tension, and this is known as capillary instability or Rayleigh-Taylor or Rayleigh-Plateau instability. And yes, I think this is called Rayleigh-Plateau instability. And but more commonly, it is known as capillary instability. Uh, and there is also something which is known as Kelvin-Helmholtz instability, which says that if there is a relative motion of two inviscid fluid with respect to one another, then there is an instability. And you can say that basically in Kelvin-Helmholtz instability, it is the motion of one fluid with respect to one another that causes the instability, which is the main cause of instability. And there, in KH instability, uh, surface tension actually acts as a stabilizing agent. In contrast to capillary instability, where surface tension is the result in which actually causes the breakdown of the jet into droplets. Okay, uh, you can do a very nice experiment in which, and that's a very feasible experiment which you can perform, is that you can take three fluids, for instance, water, kerosene oil, and let's say silicone oil. And these fluids you can arrange in the increasing order of viscosity. For instance, water is least viscous, then comes kerosene oil, and then silicone oil is the most viscous fluid. And then what you can see is you can put them in a container, and then the container must have a knob where you can allow the fluid to basically come through it, okay, come through the knob. And then you can see that for a given flow rate, water will break down first. That is, first meaning from the distance. So it will break down at a shorter length from the distance of the knob with respect to silicone oil, in which the breakdown will occur much later. It is much below. Okay, so actually this capillary instability is also governed by viscosity. That is, the breakdown is governed by viscosity, although surface tension is the reason why this instability occurs. But viscosity also plays a key role in determining the point of the breakdown. So eventually, any jet that is coming, any jet that comes out of the knob will eventually break down at some point. But viscosity actually decides the position from the knob when this breakdown would take place. And as I said, a more viscous fluid would break down later on than a less viscous fluid. And this is a simple experiment that you can do at your end. And actually, you can do a very, very rigorous analytical treatment to actually prove this. Okay. Similarly, you can show that for a given fluid, you can vary the flow rate, and the flow rates will also dictate where this breakdown would take place. Okay. For instance, if the flow rate is less, the breakdown would take place much earlier with respect to the case when the flow rate is more. And this is, I think, physically more interpretable than the first case. Okay. So these are some experiments that you can. So these are some tabletop experiments that you can perform at your end to learn about this instability, which is known as capillary instabilities. Maybe not now, but maybe in my YouTube handle, I will try to show you the analytical analysis of capillary instabilities in some other time. Okay, you can, if you are interested to learn, that is not a part of this NPTEL session or this course. But if you're interested to learn more, you can. I'll be happy to post this as a separate video where you can see that from my YouTube handle here. Okay, that is, I will show you the analytical analysis of capillary instabilities. This analysis is a little bit cumbersome because now it involves an interface which is deforming, and ultimately there is a breakdown of this interface. And that's the reason why you need to use interfacial boundary conditions. For instance, there are boundary conditions like kinematic boundary condition, which roughly, it's a boundary condition that people use for fluid interfaces. And this kinematic boundary condition, in general says that a fluid particle which is at the interface should always stay at the interface unless and until there is a breakdown of this interface. This is what the kinematic boundary condition says. And you also need to use another couple of boundary condition. For instance, you need to use something which is known as tangential stress balance, and then you can also use something which is known as the normal stress balance, and things like that. Yeah, so these are some additional interfacial boundary conditions that you need to use. Uh, so one is the kinematic boundary condition, the tangential stress balance, one normal stress balance. So these boundary conditions you need to use, and in this boundary condition you will have variables basically of the perturbations, and also you'll have the governing equation, for instance the Navier-Stokes equations and the continuity equation. So these equations are now subjected to these boundary conditions because now we have an interface. Instead of a solid surface, we have an interface. So that's the additional complexity that comes. That's the reason why we'll not discuss this here. But and also you need to learn how to apply this tangential stress balance and normal stress balance and kinematic boundary condition basically. But if once you learn, you will have a nice analytic, and in fact you can show that capillary instability is all will also in the regime of linear stability analysis, it will eventually form an eigenvalue problem where you need to basically calculate the eigenvalue eigenfunction pair, just how we did for the Rayleigh stability equation, or just how you guys saw for the Orr-Sommerfeld equation in the lecture classes. Okay, and the similar treatment also goes for Kelvin-Helmholtz instabilities, where now you have, so in capillary instability you can take one fluid to be water, or let's say kerasinol, and the surrounding fluid could be air basically. So that to some extent simplifies your analysis. For instance, you can consider that the velocity of air is 0, and that greatly simplifies your analysis in capillary instability. But in Kelvin-Helmholtz instability, you cannot. So basically, we consider two generic fluid. For instance, there is fluid 1 and fluid 2, and there is a relative velocity of fluid 1 with respect to fluid 2. Okay, and then also you have to use the same interfacial boundary condition as I discussed. But now since we have another fluid in case of air, so certain assumptions cannot be relaxed that we use, considering the fact that it was air in the previous scenario, but it cannot be done in Kelvin-Helmholtz instability. But again, the idea is same. You will just form an eigenvalue problem because of the fact that you will eventually see that in all these instabilities problem, in the limit of linear stability analysis, the governing equations are linear, and the boundary conditions are also homogeneous. I'm sorry, the governing equations are homogeneous and the boundary conditions are also homogeneous, which is again the perfect recipe of an eigenvalue problem. Okay. All right. So these are a couple of examples of instabilities that I just said. Apart from the conventional instabilities of parallel flows, inviscid parallel flows, or viscous parallel flows, these are certain examples that I thought I should speak out. And so there is a very good book by Dredgen and Reed. I think so the name of the book is Introduction to Hydrodynamic Instabilities. I think that's the name of the book. Written by Dredgen and Reed, and the publisher is, I think, Cambridge University Press. I'm not sure. I need to look out. But you can read this book at your end, and this helps basically to understand all these problems in a much better way. Okay. But what we will do today is, in the remaining time that we have, we will try to see how to solve a simple eigenvalue problem. Okay. And this will be the end of the topics that we have learned so far. And finally, we'll do a quick recap of from week 1 to week 12. That is, I'm sorry, week 13. That is something that we learned. We'll do a quick recap of whatever we learned, and yeah, I think that should be the end of it. Okay. Okay. So the agenda for this week is we'll try to see how to solve an eigenvalue problem, and then lastly, we'll do a quick recap of the course that we learned. Okay. But before that, I'll stop for a couple of minutes. If you have any questions, you can feel free to speak out. Okay. So what we will see today is that we will we'll be learning how to solve an eigenvalue problem. Okay. So actually, I would say there are two ways to solve an eigenvalue problem. I mean, two broad ways, I would say. One is analytically, and this we will see how is it done. And the other is if there is no analytical solutions to it, the only resort that we had that we commonly go for or we commonly try is numerical solutions. Okay. So I'll give you a flavor of both by considering a simple prototypical problem. But broadly, these are the two ways how these are the two ways how we saw that we use to solve an eigenvalue problem. Okay. So let's consider. So what we'll do is we'll consider a differential equation of this from d2u by dx2 plus c square u of x equal to 0. Subject to the fact that let's say my x varies from 0 to 1, and within this domain I have the boundary condition that u at x equal to 0 is equal to 0, u at x equal to 1, this is also equal to 0. Okay. So what you can appreciate is that the governing equation is homogeneous because u equal to 0 satisfies this governing equation, and the boundary conditions are also homogeneous. Okay. Which is again a perfect recipe, which is again the perfect recipe of the eigenvalue problem inside the domain where x varies from 0 to 1. So that is something that I'll write, that the governing equations are homogeneous and the boundary conditions are also homogeneous. Okay. So this means that u of x equal to 0 is a trivial solution, but we are not seeking for trivial solution. That means we are seeking non-trivial solutions where we will see that only for some specific values of c, this equation, only for some specific values of c, this equation will be satisfied. Okay. Where you can now sense that this c is indeed the eigenvalue of the problem and this u of x are the corresponding eigenfunctions. Okay. That we will that we'll try to solve for. So then how do we solve this? So since this equation is an ODE, so this is an ODE first of all, and it's a second order ODE which contains, it's a second order ODE with constant coefficients. Therefore, we know how to solve this analytically. So what we'll do is we will substitute u of x as some, as what? As some, e power some kx. Okay. Then I know that my du by dx is going to be k e power kx, and the second derivative d2u by dx2 is going to be k square times e power kx. And then I'll just substitute this into my equation 1. Insert of boundary conditions 1a and 1b. I'll just substitute it. That is, I'll substitute in 1 this form of u. What I'll get is d2u by dx2 is k square e power kx plus c square times I have u of x, which is e power k, and then this is equals to 0, which means I have that k square plus c square e power kx is equal to 0. And then since e power kx cannot be equal to 0, but because that then it becomes a trivial solution, this means that k square is equal to minus c square, which means my k is equal to plus and minus of I times c, where I know that my I is equal to square root of minus 1. Okay. So that's it. That's the value of k that we got by, that's the value of k that we got by considering the form that u of x equal to e power ks, which means that the two independent solution for u of x would be a power a some, let's say a1 e power k1, which is, let's say, icx, plus a2 e power minus of icx. Okay. But the good thing is that I can always write e power I theta as cos theta. I can write this e power I theta as cos theta plus I times of sine theta, which means I can write this solution in another form. I can represent this or recast this solution in another form as a1 cos cx plus b1 sin cx. Okay. That is simply because I can expand this always in terms of cos and sine. Okay. So this is the solution that we get uh, by solving the ODE. Right. So now let's use the boundary condition and see. So what I have is I have u at x equals to 0 is equal to 0, which means what do I have? I have, so when I put x equal to be equal to 0, the first term stays, the second term disappears. So I have a1 to be equal to 0. Okay. This is one of the constants that we got. But if we use the second boundary condition, this is where things become interesting. Because if I use this second boundary condition, I have u at x equal to 1. Okay, this is basically equal to so what do I have? So I have u at x equal to 1. This is equal to 0. Okay, which means what? Which means that if and I know that a1 is already equal to 0. This means that b1 sine c, okay, is equal to 0, but b1 cannot be equal to 0, because if b1 equal to 0 and a1 is already equal to 0, then we'll just end up getting a trivial solution, which is not what we are looking for, which means that sine c is equal to 0, since b1 is not equal to 0. Okay, this means that c is equal to n pi, where n can actually take values like plus minus 1, plus minus 2, and like this. So I have the solution for u of x as some bn sine, cnx, where cn's are just n pi's, where n goes from, plus and minus of 1, plus and minus of 2, up to how much of the number of modes that we're trying to consider. Okay, so this is precisely the solution that you got. But more importantly, what we saw is, so this is actually the eigen function that we got. But more importantly, what we saw is that we also got the eigenvalue, which is equal to n pi. Okay, and this is what actually we look for in stability problem, because it's the eigenvalue which says that a given base flow will be so a given perturbations, or the perturbations that are present in the base flow, they will grow with time or they will decay with time. Okay, so you can see that. So this is the eigenvalue that we got, and this is the corresponding eigenfunction. So you can see that only for some specific values of c, that is only when c is equal to n pi, this equation is satisfied. Okay, and this is indeed the hallmark of an eigenvalue problem, that only for some specific values only of the eigenvalue, the equation, you will basically get a solution of the corresponding eigenvalue eigenfunction pair. Okay, and this is how, and this is exactly what we get when we solve an eigenvalue problem. Okay, at least analytically as of now. All right, so I'll again stop here for some time. I hope so. This is fairly straightforward, but you should at least try to understand that only for some specific values of c is where the equation which governs how u of x basically varies with time is satisfied, and that is exactly the hallmark of an eigenvalue problem. Okay, all right. I'll stop here, and then I'll show you the second approach, which is so this is the analytical approach. It's fairly straightforward, but this is how we calculate eigenvalues uh, in our eigenvalue problems. Okay, but there will be instances where you cannot directly use analytical solutions. For instance, like since this equation was simple, we could assume u of x as some e power kx. We could assume u of x as this, and then for some specific values of c, we could see that this for some specific values of c, which is equal to n pi, this equation is satisfied. And that it was possible because of the fact that this was a second order ODE with constant coefficients with homogeneous boundary conditions. Of course, the boundary condition doesn't matter, but since it's a second order ODE with constant coefficients, we could have an analytical treatment in this case, okay? But there could be ODEs, or there could be eigenvalue problems where you cannot solve things analytically, and then what we do is we go for numerical solutions. And today I'll discuss a simple numerical solution, although there are multiple ways of solving problems numerically. I'll discuss a simple numerical approach which is known as the finite difference approach, and I'll show you how to solve an eigenvalue problem using this finite difference approach. Okay, so numerical solution is the thing that we will look now. It's the second approach that we will look now. Okay, so what we seek is, we seek for numerical solution by discretizing the governing equation. And what do we mean by discretizing? I'll explain to you in a couple of minutes. But before that, I'll stop here for a couple of minutes. If you have any questions, you can feel free to ask. Okay, so let's try to see the numerical approach now. So let's consider the same ODE that we considered. For instance, we had d2u by dx2 plus c squared u of x equals to 0, subject to the fact that u at x equal to 0 is equal to 0 and u at x equal to 1 is equals to 0. So what we do is we'll use something which is known as a finite difference method, where we discretize or we divide the entire domain, because remember my domain was from x equal to 0 to x equal to 1, and what we do is we discretize this entire domain into small points, okay, into multiple subdomains or something like that, okay, where that, so we call these points as grids. So these points are called as grids, and we take multiple number of grids, and the distance between two grids, we'll call it as delta x. We'll consider that the grids are uniformly spaced. Okay, so grids are uniformly spaced. Okay, and the distance between two grids, we'll call it as delta x. So what I'll do is, let's say I name it as my grid 1, I'll name it as my grid 2, okay, and the last grid, there is the boundary. So the last grid, which is the nth grid, okay, is grid n. Okay, now the number of grids that you now you may ask me, then how many grids should I consider, or how many divisions should I make? Now the answer to this is that the more the number of divisions you made, the more accurate your solution will be. And you will see that after reaching a certain number of grids, let's say I consider 1000 grid, if I increase the number of grids more, the solution would not change much. In fact, the solution would just vary by let's say 1 or 0.5%, and further increasing would minimize the difference between the two solutions. And when, let's say, the solution doesn't vary much, we call so this is given by a terminology. This is known as grid independence. Okay, so you need to consider that many number of grids until grid independence is reached. Okay, so that's one of the important aspects of numerical solutions. So it's like, if you consider 3 grids, your problem will not, your solution will not be accurate. Okay, but if you consider, let's say, more number of grids, let's say you consider 1000 grids, okay, and then you consider, let's say, 1200 grids, and you can see that in between 1000 to 1200 grids, your solution doesn't vary much. That means your grid independence has reached when you considered n equal to 1000 grids. Okay, and these grids, that n equal to 1 and n equal to n, okay, these are known as boundary. So sometimes, okay, in finite, so in a 1D problem, they are not called as grids because they are just 1 point. They are actually called as nodes. Okay, they are called as nodes because these are just points and not grids. But if we have a 2D problem, and there is another method which is known as finite volume method, uh, which of course utilizes discretization only, but there you need to, you need to discretize it not at the node, not at the point, but at the cell center, and then people use the terminology called grids. But here it is more conveniently to call it as nodes, so we'll call these points as nodes, not grids. But yeah, you can interchangeably use them depending on your ease of depending on the fact that you are consistent with your analysis. Okay, so so the first point is called the boundary nodes. These are known as the bonds. So the first and the last point, these are known as the boundary nodes, and the feature of a boundary node is that you already know the value of the variable at the boundary node. Why? Because you know the boundary conditions. Okay. So what you need to do is for this n minus 2 points, okay, you need to actually solve for. And what you are actually doing in numerical method is you are trying to evaluate the functional value of u at these at these nodes. And if you take the nodes so dense, then you know then you can see that your analytical that the numerical solution that you get will exactly resemble to the analytical solution that you are actually trying to that you get while if you solve this problem analytically. Meaning that if you consider more and more number of modes, the closeness of the numerical solution will move towards the analytical solution. Okay. that's that's how numerical methods work. Okay. So now the question is, how do you basically discretize? Okay. So what you do is you pick any generic node, let's say I. The neighboring nodes are I plus 1 and I minus 1. And what you do is you calculate all these derivatives in any generic node I. For instance, so for instance, you can, so I'll not prove this, but you can very easily show this by Taylor series expansion. You can show that d2u by dx2, if you write this for any generic node, you can write it as u of I plus 1 minus 2 times of u of I plus u of I minus 1 by delta x squared. Okay, plus the corrections would be order delta x squared. Okay. So these are the additional corrections that we get, because this is something that we get from the expansion, that we get from the Taylor series expansion. So you'll have some corrections, but we'll neglect, these corrections. Okay. Similarly, although we don't require, you can also write du by dx at the ith node as u of I plus 1 minus u of I minus 1 by 2 delta x, if you are using something which is known as the central difference. Okay. And then the error is also of the order of delta x squared. Okay. But we don't require this term because only we have this d2u by dx squared. Okay. So that's it. So once you write the derivative in terms of the nodal values, okay, you just need to substitute this in the governing equation. So if you just substitute it in the governing equation, so what you get is you get u of I plus 1 minus 2 times of u of I plus u of I minus 1 divided by delta x squared, okay, plus c square u of I equals to 0. And then you can do some algebra and you can write this as u of I plus 1 minus 2 times of u of I plus u of I minus 1 plus c square delta x squared ui equals to 0. And then you can write this as u of I plus 1 plus c square delta x square minus 2 times u of I plus u of I minus 1 is equal to 0. So do you see what essentially we have done? What we did is we picked any generic node, let's say I, okay, and we are writing this derivative in terms of the nodal values of u at I and u at I minus 1 and u at I plus 1. So what we are doing is we are trying to find out what will be the value of the variable at each and every node. And for that, we have picked any generic node, and for that generic node, we got one equation. So if you do the same exercise for all these n minus 2 nodes, you will see that you will have n minus 2 equations and you will have n minus 2 unknowns. Why n minus 2 unknowns? Because at each and every point of the node, the variable is an unknown which you are trying to solve for. So you will basically get a system of equations which you need to write from node 2 to node n minus 1. And in that system of equations, your unknowns are what? Your unknowns are u2, u3, ui plus 1, and you have ui minus 1 up to un minus 1. Okay? And then you have these many unknowns. Okay? And then you have a coefficient matrix which you can basically form from all, when you write basically this equation in all the nodes that you consider. Okay, this I have shown you for one generic node. You can do this for any other nodes that you consider, any other nodes that you consider in your domain, and you will get similar kind of equation. So, and similarly, you can also do this exercise for the boundary nodes, because at the boundary nodes you don't separately need to solve it, you only have the values. Okay, all right. So I hope now you understand that essentially what you will get is, you will be getting a system of equation of this form. So you'll be getting a system of equation of the form au equal to some lambda u. Okay, and where you can show that these lambdas you can basically show that, although I'll skip the details, you can do it at your end, because I just want to give you a flavor of how to solve an eigenvalue problem, where these lambdas are essentially your eigenvalues. And how do you get lambda? Basically, what you need to do is you need to form this matrix A and then calculate the eigenvalues of A. Because this is the definition of eigenvalue, that you can write any. So if you have a matrix, you can, so the fact is you can, so Ax equal to lambda x is what is the very definition of eigenvalues of matrix A basically. Okay. So what you need to do is you just need to evaluate the eigenvalue of matrix A. And this will be the eigenvalue of your analysis. And how do you form this matrix? You write these equations for each and every nodes, including, you may include the boundary node, you may not include the boundary node, that's up to you, because the information of the boundary node is already known. So it's better not to solve for the boundary node, but to solve for the unknowns. And then then you basically form a system of equations of the form Ax equal to lambda x. So the system of equation will be of that form, and then you basically need to evaluate the eigenvalues of the coefficient matrix A, which will be the eigenvalue of your problem. Okay, and and yeah, so that's typically how you, so I just give you a brief idea by taking a very simple example of how do you solve an eigenvalue problem analytically, and solving an eigenvalue problem numerically. Okay. And I'll not go into much details of this, because this is not a numerical method course, and will not discuss much more on this. But just for the sake of completeness, because we ended up getting an eigenvalue problem in the Rayleigh stability equation, I just gave you a flavor of how to solve the eigenvalue problem. Okay, how to solve a given eigenvalue problem, both analytically and numerically. Okay, so this ends our discussions of this course, the live interactive sessions. What we will now do is we will do a brief recap of what we learned from week 1. So what we did is we started off with very basic fluid mechanics, that we learned the fundamental definitions involved in stream functions, velocity potential functions, and learned something which is known as the Reynolds transport theorem, which basically served us as a bridge between a controlled mass system and a controlled volume system. Okay, solved some problem involving Reynolds transport theorem, and then what we saw is that in week 2 we tried to understand the Navier-Stokes equation, because this is the most important set of equations that as a fluid dynamics you can appreciate. Okay, for fluid dynamics, these are just something that we do repeatedly and day in day out. Okay, so we understood what different terms in the Navier-Stokes equation means. In particular, we saw that Navier-Stokes equations are inherently non-linear, and the advection term, which is u dot grad u in vector form, this is basically the main source of nonlinearity in the Navier-Stokes problem. Okay, and then we looked into some specific cases of the Navier-Stokes equation where analytical treatment was possible. We saw into unidirectional flows, for instance, plane Couette flows, plane Poiseuille flow, And then we looked into something in week 3. We looked into uh, another important class of flows, which we call steady axisymmetric flows, for instance, flow through pipes, flow through the annulus between two rotating cylinders, Taylor-Coit flows, for instance, are something that we saw. Okay. Then we move into week 4, where we learn a very important strategy of solving problem, and this is something which is known as non-dimensionalization. And in order to solve your equation non-dimensionally, you need to do something which is known as scaling analysis, that is choosing the various characteristic scales of the pertinent variable of interest. And that's why we learned briefly how do we perform scaling analysis, okay, and what does scales means in context to in the context of governing equations, and in the context of the governing equations that we saw. Okay. And then in week 5, we went a step ahead and looked into some special problems which where we saw that there were some series solution, and stuff like that, where these were where we saw that the governing equations of these problems are PDE, unlike the governing equations until then, which are ODEs. The governing equation of these class of flows, for instance, time periodic pressure driven flow in a cylindrical pipe, or the Stokes second problem, or flow through a rectangular duct, the governing equations are PDEs. Okay. And we saw how to solve PDEs using sometimes using variable separation, or sometimes using the fact that since we are looking for time periodic solution, we we consider a specific form of the velocity profile, which ultimately converts the PDE into an ODE. And then using the appropriate boundary conditions, we basically solve for the velocity profile. Okay. That was for week 5. And then in week 6, what we saw is we solved a problem in week 6 involving two dimensions. So in week 6, we move into two-dimensional flows in case of 1D flows, where we analyze the problem of calculating the flow field past the rotating porous cylinder, which means that now we'll have two direction of velocity, u theta and ur, but luckily both of them varied as a function of r, which ultimately gave us ODEs to our problem only. And ultimately we need to solve for ODEs in this problem only. But at the same time, this was a 2D problem, which uh, we tried to solve for. In week 7, we then went into study. We basically then studied a different class of flows, which we call it as the creeping flows. And the definition of creeping flows is that your Reynolds number tends to 0. Okay, that is the inertia of the fluid is absent, and it is solely the contributions of the pressure gradient and the contribution of the viscous term is what drives the is what it was dictates the dynamics of the flow field in creeping flows. Okay. But the most important aspect of creeping flow is that since the inertia terms were absent, we could our equations, which we call it as the Stokes equation, uh, were linear. Why? Because now u dot grad u term was absent, and we looked into the consequence of this linearity. For instance, we saw that if I put two objects, which was a cone and an inverted cone, we argued that the drag on these two objects, which was just the mirror image of one with respect to the one another, was exactly the same, even though the second object appeared to be bluff than the first object. And we argued these results from the perspectives of from the perspectives of linearity of the creeping flow equations. And we said that since the creeping flow equations were linear, their drag forces are going to be the same. And this is something that we saw, and we saw the equations of creeping flows. Then we solved a problem involving creeping flows, where we tried to find the solution to the motion of a sphere in an unbounded parabolic flow. Okay. The problem was that there was a sphere and there was a background parabolic flow. What we tried to understand is that if the sphere, yeah, if we are looking for a force free scenario, that is the force imparted on the sphere by the external fluid is balanced by the direct force, then the sphere can move with a constant velocity u, and we are trying to basically find out that unknown velocity u. Okay, and we use the creeping flow equations to basically solve this problem. Okay, and the good part of and the advantageous part of this of the creeping flow equations was also the fact that we could use stream function if we are using a if we are basically solving a 2D or a 2D axisymmetric problem. And indeed, this problem, that is the motion of a sphere in an unbounded background parabolic flow, is is an axisymmetric problem that we are considering, and that's why we could use the help of stream function. And in doing so, what we did is we derived the equation that stream function satisfied, and it was indeed the biharmonic equation, which was del 4 psi equal to 0 if we're in Cartesian or cylindrical space, or it was E4 psi equal to 0 if we are in spherical space. Okay, so so what we did is we basically looked into a generic expression of stream function, and we saw that for any axisymmetric object, that expression of stream function indeed holds good. And our objective was to basically evaluate the constants by using the appropriate boundary conditions from the far field and on the particle surface. Okay, and in doing so, we also learned something which are known as the Fourier modes. Okay, and indeed in this case we had the modes of the Gegenberg polynomial, but the idea was same. The basic principle was that if I have any function, I can always represent that in terms of orthogonal in terms of orthogonal functions, and each I would say each in terms of a series of orthogonal functions, and in that series, the contribution from each orthogonal functions, we call it as modes, and we saw that these modes basically behave independently with respect to one another, and you can take a large number of modes and construct the same unknown function that you considered using these orthogonal functions. Now, if we are in Cartesian space, these orthogonal functions happen to be your cos and sines. If we are in spherical space, for this example, for instance, these orthogonal functions can be uh, for instance, we saw that here the orthogonal functions were Gegenberg polynomials. Okay. Likewise, if we are in cylindrical space, the orthogonal functions if we're in cylindrical space, the orthogonal functions were Bessel functions. You can basically show that. But this is how you construct, and again, any given unknown functions as a series of these orthogonal functions. Okay. And then I think in week 9 we went on to laminar boundary layer analysis, where we looked into the exact solution given by Blasius of the boundary layer equations. And then we looked into also something which is known as Born-Kármán momentum integral approach. And we saw that the exact solution given by Blasius and the Born-Kármán momentum integral approach resembles to a great accuracy, to a fair bit of accuracy. And thereafter, in the next week also, we studied boundary layer theory, where but this time what we did is we looked into something which is known as boundary layer separation, where we argued that the presence of a non-zero so it is the presence of a non-zero pressure gradient dpdx, which indicates, I mean, if more precisely, it is the presence of an adverse pressure gradient, meaning that del p by del x is greater than 0, is something that indicates that there is the probability, or I would say there is the possibility of a boundary layer separation. But the sufficient condition was that the velocity profile must have an inflection point. Okay, and we concluded boundary layer by learning something which is known as Faulkner-Scan wedge flows, uh, where we looked into flows past any inclined objects like cones or objects having a given wedge angle. Okay. Then in week 11 and 12, which was a recent week, we looked into a new chapter which is known as hydrodynamic stability or instabilities. And then as a part of the exercise, we looked into the stability analysis of an inviscid, we looked into the stability analysis of an inviscid parallel flows, where we derive the famous Rayleigh stability equation. And then we use certain criteria, for instance, the Rayleigh inflection point criteria, Jortov's criteria, the Howard semicircle theorem, and try to understand how the Rayleigh stability equation can be used to assess the stability of a given base flow. And since the Rayleigh stability equation was an eigenvalue problem, for instance, the equation shown by equation 14, this is an eigenvalue problem because phi equal to 0, is a trivial solution, but only for some specific values of c, this equation is satisfied. Okay, And that's the reason why we ended our discussion by trying to see how do we basically solve an eigenvalue problem analytically and numerically. I agree that in this, these solutions of solving it at least numerically, I just gave you a brief idea. I didn't show you the detailed steps because of the fact that this is not a numerical solution class. But you can look into some other courses where there are there are dedicated classes in which people teach how to basically solve an eigenvalue problem numerically. Okay, and this is where we end the course. I thank you all for looking into the lecture series, the lecture videos taught by Professor Amaresh Dalal from IIT Guwahati, and also the interactive session. Uh, I thank you all for your active participation in the discussion forum. Wish you all the best for your exams and keep taking such courses. These are I feel these are one of the most, you know, useful place for learning. If you want to learn from any time, if you want to learn at any time from anywhere, NPTEL is the best place where you can just go. So uh, keep learning, uh, keep and keep enjoying fluid dynamics or fluid mechanics. And I thank you all for attending. If you have any questions, you feel free to post it in the discussion forum. Wish you all the best for your exams, and I call it a day. And thank you all once again for watching these videos throughout this entire semester. Thank you very much.